a chance to go into a bar and say, hey, I know about Mohr circle? All right, well that's what we're going to continue with today. You remember, we were taking loading configurations that we found on a particular elemental solid, but we started with it oriented quite naturally in the horizontal and vertical direction. Typically, this is just some elemental piece of some greater object, like a beam under some kind of loading, and we're concerned with looking at one little place. We want to see what the stresses are on that little piece right there, and that's all we were doing. So the actual stresses that we see on these elements are wholly and solely a function of the loading that started the problem. So we might have some kind of normal stresses in the x and y directions, and we might also have shear stresses. In any type of problem we look at, any one of those could be pointing the other direction, or might even be zero in a problem. It's very easy to come up with problems that don't have any of those in particular. Well, I guess we wouldn't want to come up with a problem that didn't have any of those, because that's a pretty boring problem in this class. But what we were looking at, starting with Mohr circle, the whole idea, Mohr circle is just one way to look at everything, is if we take exactly the same situation, the loading doesn't change, the object doesn't change, nothing changes over here. All we're doing is looking at it at a slightly different angle, because, well, it's no different than in Physics 1 when we get a particular force in a problem, and then we pick a direction for the coordinate axes, and then we break the force into its component directions. This is sort of the same type of thing. Once we turn our coordinate system to a slightly different direction, then the forces have different sizes just because of these coordinate directions that change. Just nothing more than changing the way we're looking at things. I have to stress, and can't stress strongly enough, that the loading has not changed. All we've changed is the way in which we're looking at these things, the way in which we're analyzing the problem. So some stresses can change direction because of that. It depends on the angle and what the magnitudes of all these were. So I'm just arbitrarily picking some directions and magnitudes as I sketch these in. And we have to do that because we need to find out, are there directions where the stresses get so big that perhaps our material cannot withstand those stresses. And we might not see that if we just keep it in the horizontal and vertical direction. We need to take a different look at these things and find out just where these greater stresses lie. And once we had that idea, we set up the equations. There's a couple little parts that go into each of the equations, and a couple of these actually have greater meaning later. The average shear stress is simply the arithmetic average of the two shear stresses on the two faces. Remember, the prime designates our new angle at which we're looking at things. X and Y is the original horizontal angle. So the average stress actually comes into things in two ways. We also need this quantity. It recurs in several of the things that we come at looking up. This you won't find in any book. I made this up just because I'm lazy and I don't want to keep writing out that factor. It's just a lot easier to write this shorter part. So then we laid out that how we have the 3 equation that give us these transformed stresses, stresses at some different angle of analysis. And we blessedly did not bother with the algebra that got us to this point, but we did then get a chance to practice them a little bit, and we'll do that again today as we go through these. So all I'm doing is rewriting these so that we've got them as sort of a summary. And remember that sigma diff, it carries some meaning for us as we go through these, as we'll remind ourselves again in a second. But you won't find that in any book. It's just a way to simplify things that I invented a couple years ago just because I'm lazy. But it recurs over and over, so why not save ourselves a little bit of trouble? That's all we're doing. All right, so those are the three equations of the transformed stresses that we came up with. We also then took the next step of combining two of them and simplifying and realizing that when we did that, we got the equation of a circle, and that's the very famous and well-known Mohr circle that every young engineering student is expected to be familiar with. I'm not sure Mohr circle is all that helpful. I sometimes find it even more confusing to use, because anything we need to know we actually could find with the equation straight away. In fact, one year I didn't even teach Mohr circle, but then I got nervous that I would be putting out students that had never even heard of it, and our transfer schools wouldn't be happy with that. So I've gone back to at least showing it. It's not too difficult to step through, and it does carry some of the information. What it gives us, well, let's see, it's a circle based on center sigma average, and we use the x-axis as the normal stress axis. The radius of this circle is actually the maximum expected shear stress, because we put the y-axis as the shear stress axis with positive going down, and we'll remind ourselves in a second just why we do that. And so we've got these couple of points here. We find that there will be a maximum shear stress. Remember, what this circle is it's the locus of all of the values that we could see as we go through all of the possible different angles of analysis. So whatever those angles are, let's make it omnidirectional for now. We see that in that locus there's some angle at which we're going to have a maximum shear stresses on the faces and average normal stresses on the faces. There's also some angle where we'll have the maximum shear stress on the faces and maximum normal stress and no shear stress, because that's right on the x-axis, and there's even some face with minimum shear stresses, and any points in between are possible. That anywhere on that circle is the points that are possible for these angles. And notice that some of the points repeat themselves. They're just 90 degrees images of each other, which is this square moved it at 90 degrees, and we end up with the very same square anyway. So we don't need to do every angle. We only really need to do 0 to 90. After that, we start repeating ourselves. We also found that these original stresses can be plotted right on here as points. When we do so, of course, they fall right on the those points fall right on the circle, as any points at any angle would. And once we do that, that defines a diameter. I think the book lists those points as A and G. And when we've done that, then we have this idea of these particular angles. We've defined a diameter with our original stresses in the untransformed state, just merely lined up with whatever the orientation of the solid was. But there's some angle that brings us back to this line here, brings us back actually to that point where we have the maximum normal stresses and 0 shear stress. And that angle was called theta p. And on Mohr's circle it happens to be 2 theta p, just because every angle in the transformed equations is a 2 theta angle. And those are called the principal angles, and the stresses found there are called the principal stresses, and the directions that we get from those are called the principal planes. And we find those angles by just using some of the transformed stresses that we've got. Actually using the original stresses. And so if we happen to be at those angles, actually we can put these 3 drawings, well we have 2 drawings now. The original and now this theta p direction. And we'll have a third and a second. But we can put all those together so that maybe that helps see it, and we'll do that with a couple sample drawings. So we have our original analysis of the loading, whatever it might be. Can be positive, can be negative. Oops, that didn't work. And now at some transformed angle direction, in the same direction as that, this is our original x and y direction. Now at some angle theta p in that same direction, so we can draw it like this. We now have an analysis that tells us, that brings us up to this point right here on the circle where we're at maximum shear normal stress on one face, minimum, and with the picture I have here it just happens to be negative, so I'll draw it that way. And no shear stresses in that direction. Remember, that puts us at this operating point on the x-axis with no shear stress. There's also another angle called theta S, which, if you look at this carefully, do it a couple times, is just 45 degrees away from theta P, since it uses the same values just in inverse to each other. And that angle is the opposite direction there, 45 degrees away, so that's 90, that's about 45. And we have another analysis direction. Remember, the loading hasn't changed, we're just looking at it at a different angle. That puts us at this operating condition where the normal stresses are the average values and the shear stresses are the maximum. So we have average shear stresses on both faces, actually all faces.
Why is the stress minimum stress on the top one?
Up here?
Side. Yeah, why is it there?
Why? What do you mean? Why is it there?
Pressure there?
Why is it at that angle?
No, why is it pressure?
Because of the way the circle I happen to draw is actually at a negative.
Okay.
Because remember, once you've drawn this circle and all these points are set by whatever the original stresses are, once you've got all the originals, we'll go through a couple problems too. This axis could fall anywhere. Any of these are possibilities. The shear stress axis could fall there. It could fall over here. All of these are set by the values, mostly sigma average that puts the center, and R, or tau max, that fits the radius. So that shear axis could fall anywhere. And depending on where it falls, I just happen to draw it such that the minimum shear is a negative. I guess another possibility is it could fall like this too. Now, this is not the maximum shear because it's actually quite a bit smaller. It's this shear here, not shear, normal stress, that would be the maximum one. So, and then these are all maximum shear stresses at this second of the principal angles. So maybe we could label that one P and that one S, just to remind us which of the angles we're at. Okay, we'll do a couple problems. Just walk through together a couple problems. Yeah, I didn't do that one. Okay, including calculating the angles, what the principal stresses are, drawing the circle, as we go through each of these. And we'll end up with this type of drawing here. Okay, so come upon a problem with a loading such that we calculate on an elemental piece somewhere in the solid that we expect these kind of orthogonal stresses. We expect in the x direction that there'll be 50 megapascals in tension, in the y direction 10 in compression. Well, and I hope it's obvious, maybe it needs stating anyway, that the units on these have to be the same if you actually want it to be a circle. You can't have one direction in megapascals, the other direction in kilopascals. It's not typically a problem in any of ours that we look at, but still needs stating just in case. And we have 40 megapascals as the ordinal shear stress. And so we want to find out the principal stresses and the principal directions for these particular shear stresses. All right, we need a couple pieces. We need shear average, normal stress average, because that gives us then the center of the circle. Whether you want to draw the circle or not, we still need those because it's part of the principal stresses. So let's see, that's 50 minus 10 because that's in compression, which is 40 megapascals divided by 2 is 20 megapascals. We'll need that value sigma diff, which is the x stress minus the y stress. So that's a 50 minus a minus 10, which is a 60, divided by 2 is 30 megapascals. And then r, which is the radius, is sigma diff squared plus tau xy squared, and then screwed. So we've got the sigma, that's 30 squared plus 40 squared added square root. 60? Should be 50.
50, yes.
Yeah, 50. 50. So now we can sketch out the circle. The book says plot the points that you need and then sketch the circle. It's very difficult to get a decent looking circle. I think it's a lot easier just to simply draw the circle and lay the points out from there now that you've got them. Now put down your axes where they belong. We know that this axis goes right through the center and that that point is 20 megapascals. So both axes in megapascals. Center at 20. We know the radius is 50, so that makes this far right point then 20 plus 50 is 70. And the far left point, 20 minus 50 is minus 30. And now when you've got those, you can place your y-axis, the shear stress axis. So it'd be, if that's a distance 50, we're about 20, so that'd be right about there, give or take a little bit. It's just a sketch. And remember, the positive direction is down. Do you remember why we put the positive shear stress direction down?
Works out.
When we get these angles drawn on here, the angle in the circle is the same direction as the angle on the drawing. If we had a positive shear stress up, then clockwise on the circle would be counterclockwise on the circle, and just extra pain. We don't need extra pain. All right, so let's see. We can plot point A. There's different ways to find out what these shear stress or these principal angles are. One of the ways is to plot point A, which is sigma x tau xy, which is 50, and is this positive shear stress or negative? You have to pay attention to the directions. On the positive x face, it's in the positive y direction. That's a positive shear stress. No, it's up on the x face. And then we plot that point down. So for we go to about 50, down about 40. If that doesn't plot right on the circle, something's wrong, because this circle represents all the possible stresses at any angle. So it always should plot right on the circle itself. And so there's our angle 2 theta p pictured right there. And we can calculate that directly. Get in the right direction. I did. So that's plus 40 over sigma diff was 30. So theta p. Now notice, if you remember, the calculators don't do it, but this actually represents 2 angles between 0 and 180. If you used a chart of tangents, you would be able to pull the 2 angles out of there. At 26.6 and 116.6, but those are 90 degrees apart, which just means the our element has been rotated 90 degrees, and we get the same picture anyway. So, not one angle is not more important than the other. So now we can plot our first of the principal transform stresses by actually putting in some of these values. At 26.6 degrees, which is about what that looks like, we know that the maximum stress will be 70 megapascals. The minimum will be the minus 30. And at those points, there's no expected shear stress because we're right on the x-axis. And the other principal direction, tangent to theta s, is minus sigma diff over tau xy, which is 45 degrees off of this anyway, minus 18.4 degrees. So we know that this is theta s minus, the minus is indicates the clockwise direction below the x-axis. And we know at that angle, all faces will have the normal stress of 20 megapascals. We know it's in tension because the center happens to be a positive 20. It might not always be. We'll do a couple problems where things fall in other places. And we know the maximum shear stress at that angle maximum shear stress at that angle is whatever the radius was, which is 50. So if you have a material that's very, that might be oriented at that angle, some bias in the material, like there is with wood, there's very clearly a directional bias with wood because of the grain. If it's weak in shear, you wouldn't want that grain oriented in this direction. You'd want it oriented in this direction where there is no expected shear stress. And so you can selectively place the material such that it withstands these stresses the best. Definitely the case with things like carbon fiber, where the fabric, the carbon fiber fabric itself is just a woven fabric. Very definitely has a strength bias, a directional strength bias to it. And they carefully design the direction in which they lay down I think it's called the warp and the weave of the material. All right, that's one example. It just happened to look very much like the other sketches we'd had, where the vertical tau axis, shear stress axis, fell just inside the left-hand side of the circle. Just coincidence, just to allow us to comfortably get into some of these problems. But now we know what the principal angles are. These are the principal planes, those directions, and the principal stresses on those. Questions on that before I clear the board and we do another one? Let's do this one here, a more of a design-oriented one that shows that we don't always concern ourselves with these principal angles. Sometimes we are more concerned with other angles. So imagine a steel pipe that we expect to load in the axial direction down the length of it, and it looks something like that. So we'll give it a 12-inch outer diameter, 1/4 inch wall thickness, and we're going to load it axially, so we'll have to probably put a little cap over it, give it some good solid base. So once loaded, it's going to look like that, and that'll be 40 kips. Now the deal is, this pipe was made by starting with a triangular piece of steel, rolling it up, and welding the seams together. And you can do this kind of thing with a piece of paper, maybe you have before. Take a long triangular piece like that, and then roll it up, and you'll get a tube with a seam that goes around the piece spiraling. Like that. Exactly the way the tubes inside of paper towel rolls are. If you've ever taken those out and then chased your little brother around the house, hitting him with it, Tom, once in a while. You'll notice that after you've done that for a while and the thing starts to come apart, you see that it was made out of a single piece of paper that was spirally wound together. So that puts this, what'll be a welded seam on there, have to weld the two pieces together all the way around at a particular angle. So let's assume that that weld, which goes around the piece, is at an angle of 22.5 degrees, which would actually be the angle on this original piece. So we need to calculate what the stresses are going to be and then look at them at this 22-degree direction to make sure the weld's going to be strong enough to hold. Oh wait, sorry, there's more load to it. There's also a torsional load. A torsional load of 80 kip inches. So what we want to do is look at this loading, look at some elemental piece in the ordinal directions, because that lines up with the solid itself and the loads, and then take a look at the stresses at an angle of 22.5 degrees. All right, so we'll call that the y direction, and this the x direction. So we have a normal stress in the y direction because of this compressive load over the area that's supporting it, which is the cross-sectional area of the pipe itself. So we'll need that value, but that's pi times the outside radius minus the inside radius squared. That's 9.23 square inches. That's this area. That's the area that's supporting that load. And the load itself is with 40 kip over the 9.23 inches squared. So that's easy. We could have done that in the first week. 4.33 KSI. So that's back. That's stuff from a long time ago. That's easy. Now there's a shear stress due to this torsional load. Whatever this load is trying to twist the piece that way. That's going to tend to make our little elemental solid cant to the right, I guess, if you will. And we know how to figure out what that is. That's tau c over j, where j is the polar moment of inertia. And hopefully you remember how to calculate that. It's in the book. That's comes out to be like 318.7 inches to the fourth. Remember, that's like a 1/2 pi times CO to the fourth minus CI to the fourth for outer and inner radii. And so we've got all those pieces now. 80 inches is the torsional load. What's C? 6 inches. As if we look at the pipe on end, we're looking here at an elemental piece out on the outer surface, because that's the farthest piece away. Remember, that's where the shear stresses are the greatest. So this is 6.0 inches, and J is 318.7 inches to the fourth. Gives us kips per square inch, KSI, just like what we want. and that's 151, 1.51 KSI. And so now we can draw our little elemental piece. We're originally lining it up in the direction of the loads and the piece itself. We know it's going to have a compressive normal stress of 4.33 KSI in the y direction. That's because the load is in the y direction. And then because of this torsion, the torsion on the piece there is going to try to twist the piece in that direction. If this was made of rubber, you describe that little circle on there, I mean that square on there, and then twisted this thing, you'd find it sheared in just that direction. So that gives us then the direction to go with the magnitude that we've got there, and once we've got that, we've got the other faces. And so that's a expected shear in the ordinal directions, the directions as lined up with the loads and the piece itself of the 1.51 KSI. All right. What we want to do, though, is look at what those become at this 22.5 degree angle where the weld exists. So the probably easiest way to do it is to just pull out those three equations and put in theta equals 22.5 degrees. So we need a couple pieces to go in there. The average normal stress is, you calculate it for me. What do you get? Got something? Remember, it's sigma x plus sigma y over 2. Sigma x is 0. We have no load in the x direction. And so it's the 4.33 divided by 2. That 4.33, though, remember, is compressive. So this is a minus 2.17 KSI. Sigma diff is sigma x minus sigma y, so we have a minus, it's plus 2.17 KSI. And then you can fill in all the little pieces and calculate everything from the equations. What, Joe?
Where's the square coming from? Is it,
What square?
is that the base?
What square? This square?
The KSI?
This square?
Yeah.
That square is coming because we need to know what's happening at the weld. So that's where we place our elemental solid. Remember, this idea of an elemental piece is an academic one. It's one we do in our minds. We don't actually have a piece that we pull out of there. It's a piece that we look at of size delta x, very small dimensions, and to see what the shear stresses are on that piece. No, it's not down at the base because we're looking at the weld. It's this little square here. So you can put those pieces in the equations. Sigma x prime, we're now looking at an angle of 22.5 degrees to see now what the stresses are, right lined up perfectly with the weld, and that's going to be the sigma x prime there that we come up with. So that's sigma average times sigma diff cosine 2 theta, where theta is the 22.5 degrees, plus tau xy sine theta, 2 theta. And you can put all those values in because we've got them all now. Just put them in, calculate it. You should get 0.423 KSI. So very, very small expected stress in the x direction, and it's positive, so we know that there's a slight tension there. Draw it small. We don't know what the other ones are going to be if we want to sketch these to scale, but you got to figure if we're working with 4.3 and 1.5, that 0.43 is going to be pretty small in the diagram. So we put it that way. Sigma y prime. So that, remember, is a normal stress along the length of the weld, which is not really the direction you worry about a weld failing. You're more worried about it failing because of normal stresses transverse to the weld or shear stresses in the direction of the weld. So this one we didn't expect to be very important. It's not the direction we'd expect the weld to fail anyway. So we need to calculate the other pieces. So, oops, that's in a minus. So, just taking the equations as we had them before. Another set of equations that you can save a little time in your life if you want to have them tattooed them somewhere. You don't have to keep looking them up. We've got all those values. Remember, theta is 22.5 degrees. We put them in, calculate it. We get minus 4.77 KSI. So we can draw that on the side. Solid. About 10 times bigger than in the x direction. 4.77 KSI. And compressive. Those stresses are tending to actually hold the weld together. Remember, our weld goes right down the length of that thing, like that. And then the shear stress that we expect at this weld angle, we've got all those pieces as well. No, minus sigma diff is behind the minus sign. Minus sigma diff sine 2 theta minus tau xy cosine 2 theta. That's just a straight, plus tau xy. That's just a straight component, trigonometric components there. So we get minus 0.467 KSI. So pretty small shear stress, but it's up to the technicians, I guess, to determine that actually is something this weld can withstand, because that will depend upon the type of weld, the material, the quality of the weld. And it's a negative, so we know which direction it goes.
Oh, wait.
Sorry?
Sorry.
So we know that that shear stress is going to be 467 KSI. And probably as part of this, you would have found out what the principal angles are and decided, let's not put the weld on that angle because things do get worse there. 22.5 degrees is a very easy angle to make, half of 45. So it's easy to measure, easy to cut pieces at that angle. And now we know what stresses we'd expect in that direction, in the direction of the weld itself. Got it? Okay? John, when you return, would you pull that door shut? It's getting a little noisy out there. Thanks. Phil, all right? You're squinting at it. You okay with that?
Yeah. I was just looking at the diagram.
Okay. No reason on this one to draw a Mohr circle. There's no great value in it, but you can if you want. It'll just show you the same thing we got here. It'll show you where this point was, and then we moved 22.5 degrees off of that, which is not the same as going from the point A that we've plotted before with these values to the x-axis, the normal stress axis. That's the principal angle. That's not what this is. This was just an angle that was of concern because of the way the piece was constructed. All right. Comfortable with that then? Samantha, all right? Pretty straightforward. Some of the problems look a lot harder. I know the circles can sometimes be a little confusing. But as you see, when we get to some real life problems, we don't always need it. All right, so let's do another problem that starts from the load like this one did, and we'll take it all the way through the principal angles, find out what the maximum expected stresses are and the like. All right, so imagine we've got some component of a piece here. It's like some bracket. We'll put we'll line the coordinate directions up with that. Oops. We don't want the origin up there, but we'll put it in that direction. So we'll put the X direction right down there, lined up with that piece of bracket arm. Y will go up, and Z will be in that direction. It helps to line things up with the piece and the load if you can. And since we're looking at sort of introductory problems, it's exactly what we'll do here. So in the Z direction, but applied at the end up here, there's a load of 150 pounds. So that's going to try to twist that piece, it's going to try to bend that piece over, and it's even going to try to shear that piece off, depending on what the piece is good at resisting. Hopefully it'll resist all of it. And that's actually in the minus Z direction. We could put that just so it's clear. Minus K hat. So it's in the minus Z direction. All right, let me put some dimensions on this piece so we know what kind of loads that's applying. This arm is 18 inches long. For whatever reason, we're going to concern ourselves with a spot right here, and that's up 4 inches from the bottom. Let me try to sketch that in a little better. That little spot's up 4 inches from the bottom and down 10 inches from the top. So the whole piece is 18 inches, I'm sorry, 14 inches in that Y direction. And that's, for whatever reason, that's the point where we want to do our analysis. We want to look at that point. Label it point H. And we'll find principal stresses and angle at point H. Point H such that it's completely in the XY direction. So if we took that picture, blew it up, here's our shaft, and point H just happens to be right there on the front of it. And that'll be in the XY direction itself. So it's not on the back side that gives a little Z component to it. It's right there on the front that if you were looking right down the Z axis, you'd be looking right onto that little square H. For whatever reason, that's where we want to make our analysis. Okay, so we need to know then for that piece what the normal stresses are in the X and the Y direction. So let's see, normal stresses in the X direction depend upon what forces are in the X direction, and the area, I guess I had to put area X because it'd have to be whatever area is in the X direction that's resisting that load. And remember, this is all a function of this outside load here. Let's see, well, we don't have any forces in the X direction. We have a force in the Z direction, but not in the X direction. So that's easy, that one's 0. So we have no X direction normal stress on that element H down the main shaft. And there's no bending in that X direction either. In the Y direction, it'd be whatever force is in the Y direction and whatever area is resisting it. And we don't have any Y force either. However, we do have some bending because this 150-pound load is going to try to bend that upper piece over, which is going to put, well, by observation we see it's going to put this in tension, this point at the front in tension, because it's going to try to push the back of this bracket over, which is going to stretch the front of the bracket and compress the back of the bracket because of this bending. So the moment is the 150 applied 10 inches away at a moment arm of 10 inches from that piece. Oh, I forgot to give you one thing. I forgot to give you the diameter of this bracket. That's 1.2 inches. So just a solid piece of round stock. bent at a 90-degree angle. So, does everybody see that moment that's being caused at this point H? It's the 150-pound load trying to bend the top of the bracket with a moment arm of 10 inches, because it's 10 inches above our point H.
And the back's going to be compression.
The back will be in compression, because it's trying to bend the bracket over that way. What's C? The diameter is 1.5. C then is the radius. It's the distance from the center. Because of the symmetry, that's the neutral axis, goes right through the center. We're distance 0.6 inches away from that, half of the 1.2. So, simply the radius. And I is the moment of inertia of the cross-section, which is the same there as it is down at H, since this is made just from a piece of round stock. So we'll put that here for our review, 1/4 pi r to the 4th, and we've got all that in there. 0.1018 inches to the 4th. All right, no y direction load to do any normal stress, just purely bending stress there. All that number, and we know it's going to be in tension, so we know this is positive. So we get 8.84 KSI. Remember when we first got this bending equation, it actually had a minus sign in it. You have to look at it by inspection to know whether it's going to be positive or negative. We can tell by inspection that at the front of the piece where H is, that'll be in tension. So we know this is a positive stress. And so we can now draw that in, 8.84 in the y direction. Is that KSI?
Yeah.
Yeah. Yeah, 150 pounds. Yeah, it'll be KSI. Okay. Then we also have the fact that this 150 pounds is out at 18 inches. It's trying to twist that whole piece. It's trying to twist the piece in that direction. We know that that's going to cause a shear stress like that on the elemental piece because of that twisting motion, because of this torque there in that direction, to go with the moment that we had, which I guess would be in the z direction, which I can't draw because we're looking down the z direction in that picture. But we know how to figure that shear stress due to some torsional load. The torsion is the 150 at 18 inches. So it's the force is 150, the moment arm is 18. So we know what that load is. C is the same thing because our element H is out at the very edge of the material. And J, let me squeeze it in here, is actually 2 times I, if you remember. And so it's twice that 1018, which is 2036. And so we can calculate that now, that shear stress, it's 7.96. All right, you can figure out the principal stresses, the principal angles, and sketch Mohr's circle, and sketch the two principal direction elements that goes with this, the P element and the S element. That's your task, and we'll make that a get out of class question for the weekend. Find the principal stresses and their angles. Sometimes said find the principal planes. Sketch Mohr's circle. And sketch the two elements P and S at the principal angles. And that's your task, should you decide to accept it. But this is an mission impossible, so you have to accept it. Okay, and then we'll do all that together. If you get it right and you get it early, you can go. If not, then we'll put it together. So we'll need a nice circle. Oh, I draw a good circle. Don't always put the center right in a good spot. Get that freehand circle on camera, would you? That's a beauty. Alright, so you have to figure out where the center lies, where the axes are. Of course we know where the x-axis is. It's always right through the center. The units will be KSI. Must be in both directions for everything to fit on the circle, otherwise it's going to be an oval. Good job, Joe. Darn nice circle. David, you're not a visual guy.
No, I am. I just don't have any paper today.
Well, run over to the lab and get some, or ask to borrow some. Or get a smartphone and take a picture of the board as it goes by. There's always paper available somewhere. Some of these great circles you guys draw. Nothing else. We're going to be able to say that ACC students can draw a circle. Oh, good one. Much better than last year, huh? Yeah. You practice at home? No, just grows on you. Alright, so we've got some values you can figure out. I'll make ourselves a little bit of space here. Take out the calculational part, just put the answer. All right, now we got some room to work. So, come up with the principal angles, principal stresses, and then sketch those other two elements.
This is supposed to be X prime y prime.
No,
No, it's not. right?
no, it's done from the original, these original values.
Or else how would you solve?
Yeah. Plot the point A, just to double check that your angle makes sense. This one's a little bit different than some of the other ones we've looked at. The circle looks fundamentally the same as the others, but our operating point, if you will, is a little bit different. Remember, you can find the principal angle without Mohr's circle. Just use the equations. It's just nice if these things all confirm each other. You're doing all right. Everybody's seems awful darn busy. This is wonderful. You guys off the streets, out of jail.
I know.
To kick you out of the program. You need to go work on those. You get a circle there. David, aren't you gonna do a freehand circle for us? Everybody else did. All right, let's see. Looks like everybody's getting some of the easy values. I'll go ahead with you too then. So, let's see, we're gonna need sigma average. We don't have an x direction, but we do have a y. Now, there are normal stresses in the z direction, but because of where h is, we're not concerned with those. So it's not like those things aren't there. We're just not concerned with them. So that's easy. It's gonna be 4.42 KSI. Sigma diff is x minus y, so it's minus 4.42. And R, which is actually our maximum shear stress. Everybody's getting these same numbers? This is the easy part. 9.1 KSI. Okay, so we can place some of those points. We know now where the center is. 4.42. And we know that the maximum is 9.1. Beyond that, 13.52. And the minimum is minus 4.63. Is that right? And so our y-axis, our tau axis, is right down, just about down the middle of those two. So, just by coincidence, it happened to come out about the same as all the others have looked. Could have fallen anywhere. but for the values we have, we knew it fell there. Now, point A is at sigma x tau xy. Sigma x is 0, tau xy is just under 8, and well, since it's 0 and it's on the circle, we know that point A falls right there. And so we can draw then the diameter. Point G is just what things look like 180 degrees from that, but that's still the same piece. Just this piece on 190 degrees on it. Remember, 180 on the circle is 90 on the picture. So we can then find the principal angles, and we've got that 796 sigma diff is minus 4.24, so this is minus 1.8. We take the arctangent of that, divide it by 2, because we have this angle 2 theta. Oh, this is 2 theta p. And you get 30 or minus 30?
Minus 30.
Minus 30. Which means on the picture, it's twice that, minus 60. And that's then actually this angle in that direction. It's just the shorter angle. We could go the other way like we did in all the other pictures, but that's 180 degrees opposite. It's just the very same picture, 90 degrees on its edge. So you're just getting the same thing. It's redundant to go more than 90 degrees around. All right, so we know at that point that what the stresses will be, and so we can draw that in. We're almost done. Let's see, where's a good place to draw it, I guess. Put the original one there. And at minus 30 degrees, which is about like that, we have our P direction. And we know there that the principal, so that'll give us the X direction, so that's a minus 4.63. The maximum is on the other side. That's in tension, 1352. All of those in KSI. And then in the same way we can figure out what theta S is. It's just 45 degrees off of that, so that's what, 14.9, is that right? I didn't even write it down. Yeah, 14.5 degrees. And that's our S direction. And we know there we have the average normal stress on each face, which is a positive 4.2. So we sketch that in. 4.42. And at that point also we have the maximum shear stress, which is 9.1. And so we can sketch all those in there.
You made sigma, that's sigma y, right?
What, this?
Yeah.
No, that's sigma, well, it's either sigma. It's just the normal stress as plotted. When we plot point A, we use sigma x, which for this problem happened to be 0, which, that's why we're right on this axis.
Oh, that's right, because of the totals.
This point uses sigma y. Sigma y minus tau xy, which is the mirror image of that point across the circle. Okay? So good luck in the bar in Warrensburg, where all the engineers go. Talk about Mohr Circle. Maybe they have a Mohr Circle video game we could play. Now that Pong is gone.